Hello, everyone, and welcome to today's exciting webinar. I am Tim Stark, a professor of civil engineering at the University of Illinois at Urbana-Champaign and the technical director of the Fabricated Geomembrane Institute. This is our 10th webinar of 2020, and the remaining 5 webinars for 2020 have already been scheduled with great speakers and timely topics, which are available on the FGI website. And the next webinar will be described on the last slide of today's presentation. During today's webinar, we welcome questions and comments, which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speakers will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar. Today's webinar speakers are Ryan Berg and Jim Collin. Ryan is president of Ryan R. Berg and Associates, and he will start the webinar. Ryan is an internationally recognized expert in the design and construction of reinforced soil structures and in the use of geosynthetics and civil engineering applications. Jim Collin will follow Ryan and is the founder of the Collin Group. Jim is also an expert in reinforced soil structures. The title of today's webinar is Yeager Airport Reinforced Slope Failure Case History, which is an important and timely topic. Ryan and Jim, thanks for squeezing this webinar into your busy schedules and joining us from Minneapolis, Ryan, and Jim from the Washington, D.C. area. So Ryan, the webinar controls are yours, and we'll see you at the questions.
Thanks, Tim. Good morning, everybody. I'm going to start out the presentation and give you some background information on this project and take you through design, and then I'll turn the presentation over to Dr. Collin. The purpose of this webinar is really to share the lessons we have learned from the forensic evaluation of this failure. And again, this was the largest reinforced slope structure in North America. The information being presented is from the work by the Collin Group, which performed the forensic evaluation, which included extensive field exploration, laboratory testing, detailed engineering analysis, all of which took approximately 2 years. So we're going to try to give you a summary in 45 minutes of our 2 years worth of work. Let's start at the beginning. Construction of the Yeager Airport near Charleston, West Virginia was initiated in 1944 by leveling several hilltops and filling in the valleys between them. This resulted in at least 130-foot deep cuts and fills up to 210 feet high. So quite a varied subsurface condition here at this site. In 2005, FAA regulations required the extension of runway 5 and the construction of an emergency arrest system for airplanes. And we're looking at this photo here, this overview photo of the project. The extension was completed to support, again, this EMAS structure, this emergency arrest system, and was completed by building a 1-to-1 reinforced soil slope on the southeast portion of the runway and a 2-to-1 conventional slope on the southwest portion of the runway. Here is a view of the completed structure from up on top in the EMAS system. The EMAS are membrane-wrapped, lightweight concrete blocks of various thicknesses and of various densities, and they're designed to stop a plane in case there's an emergency. Does this work? Yes, it does. In 2010, a Bombardier CL-600 plane made an emergency aborted takeoff. It was carrying 34 passengers and crew, and they were saved by this EMAS structure from falling off the 270-foot high end of the runway. All right, back to the construction. This is a topographic view of the planned extension. Here is the extension following my cursor here, the EMAS structure up on top, the existing contours at the time, and the toe of the proposed 1-to-1 slope here in this blue line. So you start getting some idea of the elevations that are being handled here. Here's a close-up view of the proposed one-to-one slope, plan view of it with the pre-construction boring layouts. And these were the planned borings. The actual borings, B4, 5, 10, and 11 were not drilled due to access problems. So that resulted in little information being found at the toe of this slope. I should mention that the subsurface investigation work, the conceptual design, the detailed design, the preparation of plans and specifications, and the construction observation were all completed by one single engineering entity. When we got into the forensic evaluation, we found there was no formal detailed geotechnical investigation report. There were boring logs. Some few of them were missing, but for the most part, that's all we had, boring logs. Again, we did not see very many borings below the toe of the proposed slope. In some of the borings, groundwater was encountered. We felt in our evaluation that this should have warranted further investigation or inclusion of drainage in the design of the reinforced soil slope. Borings also found shale in several locations, ranging in strength from soft to very soft to medium hard. Again, in our investigation, we felt that these was not well investigated in regards to stability of the slope. Likewise, there were coal seams identified. We felt, again, those were not very well investigated in regards to effect on drainage and on stability. Our investigation also found, to dig far enough back, you could find geologic maps showing past landslides just below the toe of this reinforced soil slope. This, in our investigation, did not show up in any of the documentation. Okay, so that's some of the background. Let's jump into the design. There was not a formal design report for the reinforced soil slope. What there was in the files were computer outputs from the stability analyses. And from that, we saw that the engineer of record set a minimum design factor of safety of 1.3. Was this high enough or not? Well, when you take a look at industry standards, no, this is not high enough. And we felt it was not high enough because the cost and consequence of the failure were very large. The cost to repair was much greater than the incremental cost to construct a more conservatively designed slope. And we felt that the geologic conditions were not very well understood at this site. So we felt a safety factor of at least 1.5 to 2.0 should have been used. But again, the target safety factor is 1.3. Here are two tables of the design properties used in the stability analyses. Reinforced fill friction angle 36 degrees, retained fill friction angle 36 degrees, foundation of 40 degrees. And the reinforcement that was planned and used in the analysis was a high density polyethylene geogrid. 3 different grades were going to be used, P1 through P3, 3 different ultimate strengths. Their partial reduction factors are listed here, as well as their soil interaction properties. And this resulted in grades of geogrids with long-term strengths of 2,900 to 3,800 pounds per linear foot being planned for the design. Let's look at a layout of the design, but first a conceptual sketch of the design. This was found in the files as well. This was an early concept of the design before detailed analyses. And I want to point out 3 items here on this. First, there's a note here that the toe of the reinforced slope was to be founded on bedrock. You see here back cut benching of the back cut, and we see a bench front faced. Neither of these 3 concepts, however, were carried into final design. This is an elevation view of the final design. We see the 3 grades of geogrids that are used at various spacings as we go across the top of as we go from bottom to the top of the slope. Different embedment lengths as listed here for the reinforcements, again, a function of the height of the slope. And this large V notch here is the hinge point where the slope wrapped around the southeastern corner of the runway. So we have some 3-dimensional effects here in this project as well. Let's take a look at a cross section at this maximum height structure. And at the maximum height, the planned slope height was 228 feet. The reinforcement links were constant over the height of that 228 feet. and were planned for 175-foot lengths of reinforcement. A 1-to-1 slope face again. And what the plans did not show, and what the specifications did not talk about either, was how they were going to handle the rock that was very shallow beneath the existing slope face here. So that really wasn't addressed. It was finally addressed, obviously, in construction. How are they going to remove the rock and replace it with fill and grid, not remove the rock? That was not directly addressed in the plans and specifications. The fill material was from on-site sources. Some of it was processed material to eliminate very large material was utilized directly adjacent to the geogrids to minimize installation damage, and larger material was used between those lifts. When we looked at that V-notch on the elevation view of the slope, we saw, again, it came down to a V-notch, and when you go out to the field to build that, that really wasn't constructible. You couldn't start down at the bottom of the V to construct a reinforced fill. So instead, when they got into construction, the contractor took the lower 10 feet or so of the proposed slope, filled it in with rock, and created a bench large enough to be able to start placing fill and the geogrid soil reinforcement. Here's a shot during construction. You note the haul road that's coming down to bring material down from the other on-site location to the fill area. And also we see here some water seeps. They were noted during construction at different elevations, and granular trenches were constructed to carry this water to the edge of the reinforced fill. However, the effectiveness of those is debatable. It's another shot during construction of the geogrid being installed. The actual material that was installed was a coated polyester geogrid, so something different than what was assumed in design. And as far as the embedment lengths, this maximum height section, the geogrid was carried back typically to whatever could be ripped out with a bucket, and that established what length of geogrid there was. However, we do have this haul road for bringing material down from the top, and in some locations, that haul road impeded the embedment length of the reinforcement as well. Again, a 1-to-1 smooth face. The reinforced fill was covered with a green grid afterwards or during construction to prevent erosion and to stabilize that face. Here's a good shot during construction. You can see the large truck here as far as scale of this 240-foot high structure. This is the reinforced slope on the right-hand side that has a green facing grid attached to it, and then the 2-to-1 conventional slope on the left-hand side. Here's a completed structure. The E-mass is installed on top of the reinforced soil slope we see here. A shot from up above. Again, these are membrane-wrapped, lightweight concrete blocks that are used to catch airplanes. And another aerial view of the completed structure. The actual as-built structure, when we take a look at that across section, we see the grid lengths down at the lower portion of this maximum height section were as short as 75-foot in length, as opposed to the planned 175-foot lengths. Again, the lower 10-foot was placed with a rock fill as opposed to reinforcement due to constructability. And the geogrids that were used were polyester geogrids, and one grade was used over the entire height of the structure, with 18 inches on center spacing in the lower portion of the slope and 3 foot on center spacing on the upper portion of the slope. The geogrid B was used, polyester grid was used in the central portion of the slope, so approximately a 13,000 pound ultimate tensile strength. It's a very high strength geogrid. Construction was initiated in August of 2005, and it was completed in December of 2006. And with that, I will toss this over to Jim to walk us through performance and forensic evaluation.
Thank you, Ryan. So Ryan set the stage nicely for the remainder of this talk. In 2006, the reinforced soil slope was completed. Approximately 4 years later was the first signs of distress that occurred in shallow superficial slides at the base of the RSS. And then in 2013, first tension crack in the EMAS was noted. That was followed in 2015 in January by noticed settlement of the EMAS. And then on March 12th of 2015, the catastrophic failure occurred. Next slide, Ryan. So again, here is the EMAS, and again, to orient ourselves, the southeast corner is where the one-to-one reinforced slope is. In this figure, you can see a brown line that diagonally steps across the EMAS. This is the location of the tension crack that was first observed in 2013. And that blue dashed line that is, you can see there, is the terminal end of the geogrid reinforcement for the RSS. So you can see that the tension crack occurred really at the back of the reinforced soil mass. So at this stage, it looked like the whole mass was engaged in deformations. Unclear whether that was settlement or a stability issue. Next slide. This is one of the superficial failures that occurred at the toe of the slope. This was in 2014. These failures occurred periodically during the life of the slope, and we were unable to determine whether these superficial failures were a manifestation of surface runoff or groundwater seeping through the face of the toe of the slope. Next slide, Ryan. Cracks in the EMAS continued to open up in 2014. And attempts to seal the open joints in the EMAS were unsuccessful as deformations slowly continued. And then in 2015, a forensic investigation was initiated by the engineer of record for the project to better understand the potential cause or causes of the deformation. Here we see a drill rig attempting a boring within days of the failure, and the rig is actually located in the failed mass, and you can see a change in elevation that Ryan is pointing out there. So at that point, we had a settlement of approximately 2 feet of the reinforced soil mass. The tension crack prior to failure, in the tension crack, we could observe the top layer of reinforcement. You can see that it's ruptured here, so already high stresses initiated in that layer of reinforcement. And then on March 12th, the catastrophic failure occurred. There were residents located below the toe of the slope that were evacuated prior to the failure. So there was no loss of life. It was extremely fortunate. You can see perhaps Keystone Drive, which is the access road to the residence there, that was blocked. The church located at the toe of the slide was subsequently taken as the EMAS continued to, or the slide mass continued to creep down slope. Next slide, Ryan. Here we can see the church there. Again, that was demolished as the slide mass continued to creep. And you can perhaps see a creek located there that was totally blocked off drainage-wise, and it caused flooding to the upstream residents on Keystone Drive. Another shot of the failure, you can see how the EMAS just really set down. It dropped to over 100 feet vertically. And you can also see here the demarcation between the 2-to-1 slope and the reinforced slope. So not all of the reinforced slope failed at this in the initial failure, but another section of that subsequently did fail. We had drone data that a drone was flown the day of the failure, and then several days later to help us map the surface of the failure. The blue line here was data from the drone the day within 24 hours of the failure. And then the red line is 3 days later, and you can see that the mass is continuing to creep down slope. Wow. Whenever I think of the Yeager failure, the first vision that appears in my mind is this photo of the headscarf. We are unaware of any RSS failure where rupture of multiple layers of reinforcements has occurred, and certainly none where 30 or more layers have occurred. The combined ultimate strength of the ruptured reinforcement shown in this photograph is over 300 kips per lineal foot. Notice also the moisture that is seeping out of the headscarf. Here you can see how the EMAS just kind of sat down below the headscarf, still intact. And here, this is the face of the slope. It was wrapped prior to failure, and you can see now it looks more like a moonscape. As I mentioned, after the initial failure, we did have another section of the RSS fail. And when that occurred, we obviously realized that we had a very unstable condition, and we had to deconstruct the headscarf before we could do any forensics or any remediation. This blue line here is our deconstruction 9 months after the failure. That work continued. It was stopped for a short period of time during the winter months, but continued excavation, and the final excavated configuration is shown at the toe by the red line, and then it works back up through. That's right. So one of the reasons it took so long to deconstruct the mass was that all of this material had to be trucked back up the mountain, back to the west side of the existing runways to be wasted on the airport property. As you might imagine, there were multiple experts involved in the ensuing litigation, and each expert needed to have access to collect samples and perform testing to document the conditions at the site. A detailed protocol was developed by the experts for all parties involved in the litigation. This included nuclear density testing and sand cone testing and the processed rock fill above the geogrids. The design, and we didn't touch on this, but the design of the structure included a 6-inch layer of processed rock fill above and below each geogrid level to minimize construction damage. And then sandwiched between that was a 2-foot thick layer of rock fill that had boulders up to 2 foot in diameter. So the forensics testing to evaluate the in-place density involved nuclear density testing and sand cone testing in the processed fill, and in the large fill, water testing. A total of about 450 tests were performed. The nuclear density test, the average in-place dry density from that testing was 122.2, from the sand cone 121.7, and from the water test 123.8, giving a weighted average of all of those tests of the material of 122 dry, 122 pounds per cubic foot at 9.3% moisture. Once we had removed the debris, when we got to within 10 feet of the failure surface, several trenches were excavated to observe and document the condition of the failure surface. The orientation of the trench was set up so that it was parallel to the direction of movement of the RSS and at the location of the highest point in the RSS. The failure surface was easily identified during the trenching process, and samples were collected for shear strength testing by all experts involved with the litigation. We performed torsional ring shear testing to evaluate the fully softened and the residual strength. The results of the testing showed that the fully softened strength varied as a function of normal stress from 19.7 degrees to 25.8, with a residual of 14 to 20. The plot on the right, the solid data points are from our testing. And then the dashed lines are correlations that were developed by Dr. Stark based on clay content and liquid limit. And you can see that there's excellent comparison between the two. They're very close. During that deconstruction of the headscarp, we also wanted to collect samples of the geogrid to evaluate its strength. Here we can see a exposed section of grid that we collected for testing. The process to do that was that we used a large excavator to excavate within 6 inches of the geogrid elevation. We then used a small bobcat to remove the next 3 inches, and then hand work was done to remove the last 3 inches. We took samples on both the east and the west of the center line of the reinforced soil mass. We took them at the start of the deconstruction at every layer, 3 foot on center, and we changed that as we continued down to every third layer, or approximately 10 feet. You can see on the right of that figure the layout for our sampling of any layer. So we did a random sampling to test for strength. This figure shows some of the results. So both single rib and wide width testing were performed on the exhumed samples. And the single rib tests are considered more representative of the retrieved geogrid that has been exposed to installation damage. Because with wide width testing, a zipper effect can occur. So if we have one damaged strand in a wide width test, it will fail first, and we see this zipper effect. And so you can see in these results that the wide width tests are anywhere from geogrid A about 10% lower than the single rib. And for geogrid B, they're about 25% lower. For our analysis of the strength of the grid at the end of construction, we used 9,000 pounds per foot for geogrid A and 10,000 for geogrid B. And if you remember, Ryan showed a slide that the ultimate strength of geogrid B was 12,870, and the ultimate strength of geogrid A was 9,950. The amount of installation damage between the two is maybe a little confusing. We attributed this, the geogrid A was really used in the upper portions of the RSS on the exterior ends of it. So the normal stress on that geogrid A was relatively low, where with geogrid B, those samples had up to, I think it was up to 10,000 pounds per square foot normal stress on those. I think that is reflected in the additional installation damage that we saw on those layers. We took 5-gallon and 55-gallon samples of the reinforced and retained soils and used a 12-inch direct shear device to determine the effective friction angle at normal stresses varying between 2,500 and 15,000 pounds per square foot. We measured the peak friction angle of 36 degrees. You might remember that the engineer of record used 36 degrees for those materials in his design. the bearing soil below the toe, above the rock, also 36 degrees in our analysis. And then for the soil rock interface in that claystone shale, we used a shear function. This is a good schematic of the forensic cross-section that we used in our analysis. The purple there is our reinforced slope with geogrid layers 1.5 feet apart in the bottom, 11 meters, and 3 feet apart in the remainder. You can see the green at the toe, which is the fill that was placed below the toe of the RSS, unreinforced. The soil rock interface that we exposed during our trenching in the shale, our sandstone behind that, and then the in situ retained fill. Bedrock mapping was performed by both hand and by drone acquired high resolution images of the rock surfaces. The prominent dip direction of the sandstone ranged from 170 to 230 degrees azimuth, and the dip angles ranged from 30 to 90 degrees from vertical. These discontinuities provided conduits that directed groundwater flow in those same directions from the bedrock directly behind the RSS into the RSS. And this was evidenced through flow both during construction and post-construction during the forensics. Next slide. All right, so let's look at the analysis. So in our stability analysis, we've used limited equilibrium analysis, and we looked at 5 cases. We looked at the initial design by the engineer of record, 175-foot grid lengths, geogrid long-term design strengths of the 2 materials actually used on the project, soil strengths as assumed by the designer with the slope sitting on a rock, and the drain condition. We looked at the impact of shortening the grids and not changing anything else in case 2. In case 3, we looked at end of construction, and for our geogrid strength, we used the exhumed geogrid strength as determined from our testing. So not considering creep or degradation, just installation damage. And then case 4 used the same conditions, except now we use the fully softened strength of that soil rock interface, and then finally with 4 different groundwater conditions. And then case 5, we looked at the effects of including creep in the geogrid reinforcement on the stability. Next slide, Ryan. So here we can see there was no, as Ryan mentioned, there was no groundwater monitoring during the design phase for any of the borings, and we had no monitoring prior to failure. So we estimated 3 groundwater conditions. We did that estimate based on a procedure developed by Hook and Bray in their rock slope engineering book. So we have a high groundwater table, a medium, and a low, and a dry. Now let's look at the results. So for our case 1, we analyzed that the factor of safety based on the assumptions was actually 1.54, not the 1.3 in the design documents by the engineer of record. When the design was revised to shorten the grid lengths, but considered it was still founded on rock, the factor of safety decreased to 1.45. When we looked at that end of construction here with a higher grid strength for the short term, factor of safety increased to 1.7. And then the real meat of it. So when we considered the fully softened strength of that interface, we see the factor of safety now drops from 1.445 to 1.15. We see that the groundwater conditions had minimal impact on the stability, right? And then we considered the creep in the geogrid reinforcement in case 5. We see that all the factors of safety are basically 1, and failure occurs. Next slide. So, summarizing, reducing the reinforcement lengths from the original 175 feet to the as-built lengths reduced the factor of safety of the slope. Failure to design and construct the RSS on sound rock reduced the factor of safety further. Not including any internal drainage system in the RSS and the development of groundwater within the RSS further decreased, but relatively small, the stability of the slope. And when the factor of safety was marginal, less than 1.15, the strength of the geogrid was reduced by creep prior to collapse as post-peak soil strengths were mobilized, resulting in a factor of safety of 1 in failure. Next slide. So we felt very good about our limit equilibrium analysis, but we really wanted to understand really the kinematics of the failure. So where were our stresses the highest first, and how did the failure progress, right? It took almost 8 years for the failure to occur. So what changed? We wanted to look at that. So we used FLAC 3D, and we did a narrow slice, 1/2 meter wide, at the center line of our trench to do the analysis. We looked at case 4, end of construction, and the ultimate strength of the geogrid was used to construct our model. Once the grid was placed, we used the exhumed strength, and then the geogrids are modeled as nonlinear cable elements that can yield and rupture, and if the strain limit is reached, its contribution to the model was removed. Next slide. So again, here's our model. We looked at the shear zone and used the same power function that we used in our limit equilibrium analysis. At the sandstone interface, the upper portion of the slope there, we used a soil rock interface of 40 degrees. And we did a parametric study there to see the effects of that shear strength there, and found that the model was really not very sensitive to that. So we felt like that was an appropriate value to use. Next slide. So this is in the strength reduction phase of this analysis. These dark lines are shear bands, and you can see shear bands near the face, right? And then this second set of shear bands, which is at the terminal end of the reinforcement. So this is where we saw the first tension cracks in 2013 occur in the EMAS. And the analysis here kind of gave us a picture of why that occurred. As strains occurred, we did develop that. The next slide shows when we did our strength reduction analysis, we reduced the strength. As we did it, we got a rupture of the grids at 3 locations. That there is within about 1 meter to 2 meters of the observed failure surface of the EMAS. And we could see the mobilization of movement in the deformation analysis, and it occurred behind and below the geogrids in the lower portion of the RSS, where the field changes were made to shorten the grids. And the deformation analysis results were consistent with our field observations. So, failure mechanism was a compound failure. Failure surface below the RSS was along that shale claystone interface. The collapse occurred after 8 years in service as the shear strength of the shale clay interface decreased from peak towards the fully softened strength. And then summarizing here, the results of the 2D limited equilibrium and the 3D permanent deformation analysis are consistent with the failure mechanism identified in the post-forensic investigation. Finite difference deformation analysis confirmed that a reduction in strength occurred along the soil rock interface during the 8 years service life of the RSS due to deformations induced by the applied shear stresses and availability of groundwater at the interface. The deformation analysis identified that the failure surface propagated from below the reinforced zone near the slope toe, behind the geogrids in the lower portion of the slope, and through the upper portion, through the geogrids in the upper portion of the slope. Tension cracks observed approximately 2 years before the failure also appeared in the stress deformation analysis when the tensile geogrid strains reached 2%. I think this was really enlightening to us. We struggled with why we saw a tension crack at the back of the mass versus the final rupture through it. And I think the deformation analysis gave us a good handle on that. And then finally, the shear strength of the soil rock interface decreased from the peak strength towards the fully softened. The lower portion of the slope underwent shear deformations, which transferred the shear stresses to the geogrid reinforcement, which resulted in deformation and creep strength reduction, resulting in the failure. And the last slide. So the airport is back fully functioning. This is the solution. Design was done by Schnabel Engineering, consisted of soldier beams, concrete lagging, rock anchors, and geofoam fill. And so this approximately 6 months ago, the airport was fully functioning again. And so with that, I'll open it up, Tim, for questions.
Great, Jim. Thank you. We've got a bunch of questions here. So hopefully Ryan can rejoin. Good, Ryan. Okay, here we go, guys. Any specific reason to select the site on this hilltop location for the airport? Were there other sites selected or evaluated in the site selection study?
I don't think historically we found any information on that from the 1940s, but it's if you've been to Charleston, it's a hilly area, and I'm sure it was just a collection of where they can find enough land and what they have to do to level it out.
Right. Yeah, Charleston's built on a river, and that area is pretty well tied up. Did the site selection process include any preliminary subsurface site investigation?
Back in 1944 or whatever?
Yeah, it looks like, yes.
Yeah, we really don't have any real information from back at the beginning, other than just some very limited articles that were published back then. So we don't know how extensive that investigation may or may not have been.
Okay, the next question is somewhat loaded. It's up to you whether you want to answer it. Can you name the design engineer?
No.
Okay, let's moving on. Any specific reason to have a steep one-to-one slope that is challenging and difficult to construct? Obviously, space was limited, but what else?
I think that Ryan and I both thought a one-to-one slope was the perfect solution to this extension. So I think we feel that it definitely could have been built successfully. Our analysis shows that, I believe, and that there were just things that went wrong that caused the failure. But when we tried to, when we worked with the airport authority to talk about ways to replace the EMAS, we both spoke about rebuilding it as a reinforced slope. It would be the least expensive solution that they could come up with. And the director of the airport turned to me and he said, Jim, if I go to the board and tell them we're going to rebuild the slope, they will fire me. So, but no, I think we felt that this was the right solution.
Okay, then let me parse your answer a little bit. You said it could have been done successfully except for some problems. I'm assuming those were the problems during construction, or can you just give like 3 or 4 bullet points of what prevented this from being successful?
Well, if we go back to the subsurface investigation, needed more information along that toe. And as that was carried into the design and specifications would have had to address how the shale interfaces were going to be handled, how deep that had to be excavated, benching the back cut into the rock, not leaving that smooth sandstone face back there. We also would have wanted to have internal drainage in the reinforced slope, and generally some sort of step facing or at least maintenance benches on the outer face of it. So there have been several features that could have been stepped up and again increase the target safety factor because of the criticality of the structure.
Okay. What was the approximate cost of the geogrid structure, the initial cost?
I believe it was on the order of $6 million.
Okay. Was the engineer of record hired to monitor the work during construction?
Yes.
Yes.
Okay. In your opinion, keeping the geogrid and structural design the same just by changing the geometry / slope, do you think this failure could have been avoided? I'm not sure. Do you guys understand that? Keeping the geogrid and structural design the same.
No, I think as I previously answered, I think the safety factor should have been increased. The detailing should have, for drainage, for benching the back cuts, for addressing the foundation, chasing out those weak shale interfaces, all would have had to been addressed to get a stable slope constructed here.
Yep.
And we did do an analysis of what it would take to get the factor of safety to 1.5 as part of our work, and it would have required double the amount of reinforcement. So it would have been, it would have been a significant increase in cost, a lot less than what was spent to deconstruct and then reconstruct, but it would have been a significant change in the cost of the structure.
Okay. What software did you use for the 2D limit equilibrium and stability method?
We used Slide 2D and FLAC 3D.
Right, but as I recall, it was Morgenstern and Price's stability method.
Oh.
Yeah.
Yes, that's correct.
Okay. The comment you made about the headscarp and the total shear force at the headscarp, Jim, you were describing it. I think you came up with a number of like 300 kips per foot when you showed the picture of the shear face of the grid. The question is, could you explain that in some more detail?
Sure, I can try. So each layer of grid, the ultimate strength of that grid per lineal foot across the face of the failure surface was 10,000 pounds per foot was its ultimate strength. So when it failed, each layer provided per foot of the face 10,000 pounds, and there were 30 layers of grid. So the combined capacity at ultimate was 300 kips.
Yeah, and these layers that we see here in this photo, they're 3 feet apart vertically.
So it had 300,000, it had 300 kips per foot of capacity. And then when things started to move and the geogrid strained, its strength reduced by a factor of approximately 1.5, and that's when the failure occurred. So when it initiated that creep strain, the strength went down, and that's when the catastrophic failure occurred.
Okay. Was there any movement of the unreinforced slope, and did you evaluate the stability of the unreinforced slope?
So if you remember, I know we showed a lot of slides, but for the unreinforced slope, when we looked at the existing contours prior to extending the runway, the 2-to-1 slope sat on a bench. So the 1-to-1 slope continued down, right? It was very steep underneath it, but the 2-to-1 slope sat on a bench. So it was pretty much a conventional 2-to-1 slope without any issues with foundation. So we didn't do a lot of analysis of that, in fact.
Right. Okay, and that dovetails to this next question. Had the bottom of the RSS been constructed on a flat shelf into rock, like you just described, Jim, for the unreinforced, would the same gradual movement at the bottom have occurred, and then, of course, failure?
Well, no, we don't think so. If there was a 175-foot rock bench, that no, we wouldn't have seen failure.
Okay. Yep. Well, this is kind of loaded. I don't know if you want to end. Did the engineer of record approve the shortened geogrids and no rock excavation in the lower portion? And maybe you want to pass that. I don't know.
Yeah, the engineer of record was. You want to go ahead, Ryan? Go ahead.
The engineer of record was on site for observations during construction. They recorded very well all of the geogrid lengths and mapped them out, so we had a very good record of all of that. However, we did not find a formal approval of shortening of the geogrid or any formal documentation on how the rock was to be handled in the back cuts. Jim, maybe you've got a little more information on that.
No, I think that's you got it, Ryan.
Okay. And guys, we're getting tons of questions. We're probably not going to get through all of these, but any reason for switching the grids from HDPE to polyester, and how to consider the contribution of strain in the LTDS calculation?
Well, I think the selection of reinforcement was probably a financial, based on costs. That would be my guess. We didn't have any documentation one way or the other on how that change was made.
But remember, Jim, the airport had a slide on the west side of one of the runways there, and they were going to repair that with the reinforced slope, and I believe they already had purchased a geogrid for that. And then when the contractor came in and proposed a soldier beam wall or some other type of structure, so I believe the airport had already purchased some polyester grid for a different slide repair.
Okay. Any insight into what amount of deformation should be used to design reinforcements? For example, 2% strain or something different?
Well, I think from our measurements of other structures, and this structure was not instrumented at all, which is a shame due to the size of it and the magnitude. But typically in reinforced soil structures, we'll see a maximum in situ strain of approximately 1%.
Okay. Jim, you mentioned the hook and bray method to model groundwater. Could you just briefly describe that?
No, I could not.
Okay.
Our geologist, Skip Watts, did that work. So I have to defer to Skip on that. So sorry.
Okay. In hindsight, of course, what would have been your approach to providing drainage behind the RSS zone?
I think I think a chimney drain right immediately behind the RSS zone, and then a blanket drain beneath it as well. I don't think that the fill material that was used, although the specs would allow up to 50% fines, the actual fill was very granular. So taking a trench out laterally, I don't think carried the water out of the reinforced slope at all. I think it just distributed it a little bit more. So again, I would go with would have thought of a chimney drain and a blanket drain both in a structure of this size.
Yeah. There are a lot of questions here about fully softened strength and the soil rock interface strength going from peak to fully softened. I don't know, how long would it take? 8 years? Did it take long for groundwater to soften the fill? Maybe this is something we should handle in the podcast. There's probably 5 to 10 questions about that. If you guys want to say something in general about it, jump in.
No, let's handle it in the podcast. I mean, I think we probably don't have time for that in the last minute or so we've got.
That's what I'm thinking. Okay, we will address the soil rock interface in the podcast and development of a fully softened condition, peak fully softened residual in the podcast. Okay. Well, that one's kind of loaded. Was cost at any point a determining factor in the choices made during exploration and for design and then construction? I think you've already answered that one, but go ahead.
We're unaware of any limitations that were put on the engineer record for cost considerations. There may have been some, but we found nothing in the documentation and in talking to the airport authority that led us to believe there were limitations put on the engineer from a cost perspective.
Okay. Any lessons learned from the limit equilibrium stability analysis of the unreinforced? How different was the factor of safety? What about the location of the failure surface in the unreinforced analysis versus the reinforced analysis?
Well, we didn't do any unreinforced analysis. We just did the RSS, the one-to-one slope. So I'm not sure that I'm understanding the question, but our analysis was for the reinforced section, the 2-to-1 slope, unreinforced. We was stable. We didn't focus on that.
Okay. You mentioned that there was insufficient exploration or documentation in the form of a design report or a design memorandum for a big project, $6 million improvement. What about peer review? Was there any external peer review for this project?
There was not, and that's another conclusion in our study, that there certainly should have been for a groundbreaking project of this magnitude, that there should have been detailed peer review.
Yep. There are a lot of questions here about the podcast and the slides being available, so let me just handle these. A PDF of the presentation slides will be made available on the FGI website along with the recorded webinar. So you can listen to it again and download the slides, and an audio recording of the podcast will be available shortly after the podcast on August 25th. What's the cost? Well, you weren't really involved in the repair, but there are a bunch of questions about the repair. For example, what was the cost of the remedial solution? Were there other more cost-effective ways to repair it? If you want to jump in there.
Well, we don't know the final cost, but we could probably get that information from our colleagues at Schnabel. As far as a less expensive fix, rebuild an RSS, as we said earlier, would be, I think, what Ryan and I would both look to do.
Yeah. Okay. There are a bunch of others. So we'll handle those in the podcast. I have about noon. So everyone, thanks for joining us. The contact information for Ryan and Jim are on the screen. If you have additional questions, you can contact them directly or send them to me. We will include them in the podcast. Ryan, if you go to the next slide, is the next webinar in our series is Construction on Soft Foundation Soils. This is the Mercer Lecture presented by Professor Kerry Rowe of Queen's University. He will give it again on Thursday, September 17, 2020 at noon Central Time. And of course, Kerry Rowe is just a fantastic speaker and researcher, so I hope you'll tune in for that. Next slide, Ryan. I encourage everybody to visit the FGI website. You'll see all the videos from the webinars, testing videos, technical papers, etc., pond leakage calculators, cost estimation comparison calculators. So visit fabricatedgeomembrane.com. I'd like to leave everybody with a final announcement that the GeoAmerica's 2020 conference will occur from October 26th to October 29th. It will be a virtual conference, so you do not have to travel to Rio de Janeiro, but there are many sessions in this upcoming conference on geosynthetic reinforcement that dovetails nicely with the presentation today by Jim and Ryan. So thanks again for attending, and thanks again to Ryan and Jim for an excellent webinar and joining us from Minneapolis and the Washington, D.C. area. Thanks, guys. See ya.